John Zink Company designs and manufactures emissions control equipment and clean air combustion equipment. Our primary goal is eliminating waste from the environment so that our customers can operate safe, efficiently, producing the products that they do. My name is Jason Harjo. I'm the design manager for John Zink Company in the Flare product group.
So my name is Bert Reelhuis. I am a manufacturing engineer at John Zink.
I'm Paul Newman. I'm the general manager for John Zink Hamworthy over in the Poole office in the UK.
We're always looking for better ways to serve our customers, to help them serve their customers.
In order to get where we wanted to go, we need to do something different. We need to reduce the amount of restrictions we had on how we manufacture things.
When you look at our manufacturing environment, it's more of an engineer-to-order environment in that we're not making a bunch of widgets, thousands of widgets per day. It's more one or two or maybe dozens of burners at a time.
We're out looking into every opportunity that we can to utilize additive to solve a problem. You can only do so much with traditional manufacturing. And additive opens up a whole new door for new designs where you have internal pathways to certain parts, where you can get more efficient mixing of maybe fuel and steam, as in an atomizer. But that's really the problem we're trying to solve, is newer designs, more efficient designs to operate our equipment more efficiently. This is a YE6 burner tip. This was installed in a thermal oxidizer burner. And in a thermal oxidizer, it's burning and creating temperature to effectively destroy waste at the end of a process. This is very critical to the function of a system because this is what's going to shape your flame to burn efficiently. This part hadn't been manufactured in about 30 years, and so the tooling was gone. And so we decided, hey, we're gonna print this part, and now we have a successful part, and we didn't have to buy tooling for it. So normally with a part like this, you're investing thousands of dollars worth in tooling, and that's just to get started. And then you have to manufacture the parts. And then there's the lead time to not only manufacture them, but ship them to you. But with the studio system, we're able to print it and debind and sinter it in a matter of weeks, as opposed to months. And it also could run us several $100s as opposed to several $1,000s.
For me specifically, the most important part of having a studio system in our shop is being able to design a tool or fixture and have it produced quickly. One example that I have here is a design from a machinist that's been with us for about 30 years. And he has these really heavy tools that he loads into his lathe. And the way he's been grabbing these parts over the years, just with his thumb and his index finger, and that's a lot of weight to load in on one part. Now on all of his tools out there at the lathe, he's got about 30 of these tools with the handles on them. They're all drilled and tapped, and he now uses the handle here to load his parts in and out of the machine. What we did is we first printed out of plastic. We tried the handles, he loved them, but over the course of a week he says, hey, my plastic part is broken. I said, okay, well, we have this metal printer, so we can print it out of metal for you, and that thing's not gonna give you any issues. It made sense to print this part versus machining it, because we would have had to take a pretty large chunk of metal and machine this down, especially to get this curvature. So it would have been time consuming and taking up our resources, where we like to focus our resources on making products for our customers. So one of the examples of parts that we're able to implement in our shop is this nozzle. It's used on our laser. Essentially, we were cutting some tube that created a lot of slag and buildup on the inside. So this is a really complex geometry. It's got multiple channels in it. So you have one port that directs the flow, it concentrates the flow of gas, and then you have another port that kind of creates a plume. You cannot make this any other way. It can only be 3D printed. The first thing we did was 3D print it from PLA. So we printed it on one of our desktop printers, we threaded it, put it on the end of that gas nozzle, and we tested it out. What we found that it was very effective, but it didn't last very long because the heat caused those ports to melt shut. Basically just disintegrated the tip. Then we went to the metal part, which we knew was going to be our long-term solution. So now this part can be threaded onto the end of that gas nozzle, so it purges the cut as it's being produced, creating a clean part that doesn't have any post-processing.
We were always pushed and pushed and pushed to try and reduce the amount of fuel we were burning. So we were looking at how we could improve this, and one of the things that we found out was if we could improve the mixing of fuel and air, we can reduce the amount of fuel we burnt. If we could create some other form of mixing using the atomizer, for example, that would create a lower flow of fuel oil, which is what we were targeting. This is a conventional atomizer. The concept is that you've got steam going into the middle and oil around the outside, and there's a mixing port that you end up with an atomized fuel oil. This is made out of a conventional piece of bar stock. The outside is machined to just give us the shape that we need, and the holes are drilled with conventional drilling machines. But you're pretty restricted on what you can do with it. When we knew that we could use additive manufacturing to create metal parts, we were still under the mindset that a round hole is the only hole you can have, because it's just ingrained in us from a design point of view. So the first thing we looked at was how we could get air into the middle. So we thought, let's remove this material around the outside of the hole and just have tubes coming from the center. We ended up with something along the lines of this. This is obviously made out of plastic and a slightly larger scale, just so that we could look at it. But it's got the ability for air to get into the center, which is what the target was at that point. And we slowly understood that with additive manufacturing, we're no longer restricted to round holes. We want to improve the atomization, so let's not make a round hole, because that's not necessarily the best way of doing it. Which is when we came up with this, which is our final design, and we've done some CFD flow patterns across the face of this to have a look at the airflow, and it is vastly improved. So using the conventional atomizer, we could reduce the flow rate of this down to about 120 kilograms an hour. And with this one, we can get down to 38 kilograms an hour. And if you imagine that's firing 3 burners, that's 3 times that over the number of ships they have, firing however long, is a huge saving in fuel oil. When you're looking at the use of additive manufacturing in the process that we were looking to achieve here, the prototyping gave us the chance of testing things very, very quickly, so that was an advantage. But the biggest advantage was simply the fact that we were no longer restricted to this simple round holes at certain angles. This, you can do anything.
Desktop Metal has a system that has a very low-cost entry point into the technology.
I think one of the biggest benefits for us in working with the Studio system is that it did not require a lot of PPE. Because of the fact you're not dealing with any free, powder metals, that it makes the process really safe and easy to work with.
Preparing the facility there's no real cost there. Basically, you plug it in and you can go.
In terms of industry applications, it's very, very versatile. You can use it for all sorts of things. There'll be a lot of gains you can get from a design perspective.
Companies that feel like metal 3D printing is too far in the future, if additive manufacturing adds value to them whatsoever, and they're not investing in it, then they're already behind.
The limits of additive manufacturing are only what you can think of creatively, right? So anything that you can think of, you can pretty much print.
Without additive manufacturing, there's no way we'd be where we are now.